Thank you also for kind introduction. So thank you for inviting me to this as exciting university. Today's talk is the title is a new frontier of the material research. And in this talk, I will show material science is much more interesting than we expect always. I will show the three talk on the subject. Okay, my affiliation is Tokyo Tech. Tokyo Tech is oriented for the science and technology area. So the Tokyo Tech has three campuses. Two is located in the Tokyo metropolitan area, as like this, and another is located in the Yokohama area. Yokohama area has 4 research lab and one department, one life science department. So this campus is oriented for research. As Frontier Research Lab and MSL are located on this campus. And maybe you know that Professor Shirakawa, who invented the electroconducting polymer, polyethylene, he is a Nobel Prize winner. He is a graduate of the Tokyo Tech and polymer department. Okay, in this talk, I will show that doping is wonderful to realize the new functional materials. Okay, and so this is the outline of my talk. And first, I'll show that the motivation and the grand objective of our research. And after that, I'll show the three examples. One is electron doping to C12F7. So I'll show that maybe this material looks as bonding. This is a typical insulator. I'll show that this material can be converted to transparent semiconductor, metal, and eventually superconductors. And the second is the most important for the practical application, is high performance thin film transistor to drive the next generation flat panel display. So this TFT is almost aggressive semiconductors. And performance of this TFT is one of the higher than that of the currently used amorphous hydrogenated silicon. So maybe within the next 10 years, this material will kick out the amorphous hydrogenated silicon in the display area. And the last one is we are now heavily involved ion pnictide superconductors. In a research area, research is almost changed from Bronze Age to Iron Age. So last week, 2 weeks ago, the largest conference on the superconductor was held at Tokyo M2S. So the major fraction of the paper are ions. The second is coppers. So nobody believes that the iron becomes superconductors. Iron is a magnetic element, so nobody believes that the iron, as people believe that the iron is the last element to emerge superconductivity. But now the iron pnictide is a mainstream for high temperature superconductors. And this last one is perspective. So why? As we are sticking to the transparent oxide. So especially my background is ionic solid-state chemistry. So especially as a build from the material, ceramics is a main field. So the classical ceramics are like glass, cement, or porcelain. So that these materials are composed of abundant elements like this. And we can easily dispose into the garbage, no problem. So the high compatibility with the environment and chemically and thermally stable. But nobody believes that this material can be a platform for active function materials such as semiconductors. So our challenge is to creates a new electroactive material based on abundant oxide. So that we call the element, ubiquitous element strategies. Okay, let me start by showing the feature of oxide in comparison with silicon. So the chemical bonding nature is from ionic, ionic, and it's covalent. So the covalent extreme is very, very simple. Silicon or diamond is a typical example. So crystal structure is very, very simple. And the tetrahedral structure like this. And when the opposite side is also simple, simple cross packing of the ions, like sodium chloride structure like this. But when covalent nature is added to the ionic nature, crystal structure becomes a little bit complex. So that we may expect the interesting structure like as nanopolar structure or the two-dimensional layer structure. If the electron is put into the cage, so that this material can be regarded as a quantum dot, three-dimensionally connected like this. So the coupled quantum dot. So when this is layered structures, if these layers semiconductor with narrow gap and these insulator with a large band gap, so the electron is confined in this layer. So the inner kind of this material may be regarded as a two-dimensional electric structure are realized here. Okay? So our strategy is to extract intrinsic properties by utilizing such a nanostructure embedded in intrinsic crystal structure of oxide. Okay? Okay, so this is a progress of in our research. I started as oxide semiconductor research from the 1993. And 1995, or not 1995, I proposed a material design concept of the high mobility amorphous oxide semiconductor. And the paper appeared in 1996. And at that time, as I presented this paper on the amorphous semiconductor conference, no response. Okay, but after that, we continued the research and we published a paper on high performance TFT using amorphous oxide semiconductors. This paper fired active research of the oxide TFT. And now amorphous oxide TFT is booming all over the world. And another the origin of our research is P-type semiconductors. N-type oxide semiconductor is not so rare. So, for example, the zinc oxide and the tin oxide are well-known N-type semiconductors, but no P-type semiconductors until 1970s. We published a paper on material design concept of the P-type transparent oxide semiconductor and typical example of the copper aluminum oxide. So at that time, we obtained the P-type and N-type. And after that, we fabricated the PN junction for UV LED 2000. And in the flow of the P-type oxide semiconductor, we discovered the superconductor of the iron in 2006. Okay. So let me start the first subject, C12S7. This is the history of the electroconductive materials. As you can see, that although so many insulators have been converted into electroconductor, except such abundant metal oxide still remain as typical insulator as described in the textbook. For example, the CaO, aluminum, and SiO2. If you choose this material as a metal or as a semiconductor, you should fail in an entrance examination. Okay? So my dream is to convert this abundant oxide to a semiconductor or metals. So that part of the material is now available in the form of the metals. Okay, this is a phase diagram of the CaO and aluminum. So both of them are well known as an insulator. Okay, the CaO and aluminum. There are 5 crystalline phases. We focus on the C12S7. So the synthesis is very, very easy. A mixture of the calcium carbonate and aluminum and heat it up and in air to 1000 degrees C, you can obtain this material very easy. And this material is commercially used component of the aluminum cement. So it's very, very easy. Most of the people, ceramic people know this material, but nobody believes that this material can be converted into semiconductors. Okay, the crystal structure of the C12S7 is quite interesting. Okay, this is the cubic structures, and lattice and band gap is 7 eV, completely transparent. And there are 12 cages in a unit cell. Okay, very, very complex structure. And the chemical formula for the unit cell is like this. The cage structure, cage wall has a positive charge of the +4. To compensate this positive charge, 2 oxygen ions are distributed at the 2 out of 12 cages like this. So the occupation of the O double- in a cage is only 1/6. 5/6 is empty. Okay? And quite interesting, the size of the cage, the diameter of the cage is almost double of the diameter of the O double- ion. Okay? So the electron of the O double- is, how do you say, loosely bounded in the cage wall. So the crystallographer called this oxygen ion free oxygen ion. Free oxygen means that loosely bounded. We focus such a crystal structure. And someone feels that this crystal structure is like a C60, but totally different. Okay, C60 is conducted by van der Waals force. Okay, but this material is connected by sharing a monolayer oxide. Okay, so in a sense, C60 is like a Western-style cottage. C12S7 is like a Japanese-style inn. All the big room is connected separated by Japanese-style fusuma. Okay, so the electron pass through. Okay, but the ion cannot pass through. Okay, so this means the electron tunnel is possible. This structure. This is pretty important. Okay? This is a single crystal of the C12S7. So the single crystal growth of the C12S7 is not difficult by tuning the atmosphere. Oxygen is absolutely needed. Anyway, this is a C12S7 single crystal. And so at first, when the C12S7 single crystal is heated in hydrogen-containing atmosphere, so apparently nothing changed. Looks white, nothing changed. But when the hydrogen-treated C12S7 is exposed to the ultraviolet radiation, what happened? This one. So before irradiation, of course, the sample is insulated below 10 to the minus 10 at room temperature. When the sample was exposed to the UV radiation, so conductivity goes up over 10 order of magnitude. And the conductivity at room temperature is almost 1 or sometimes 10. Okay? And such a conductive state is persistent. That is to say, that when light illumination stops, such a conductive state remained forever. Okay? And this is the temperature dependence of the conductivities. And it's not linear like this, but almost linear as a function of T quartered. So that this means that the conduction mechanism is not a thermal hopping type mechanism, a simple Arrhenius behavior, but the variable length type hopping like this. And this is a photograph of the sample, transparent insulator and the transparent conductors. Okay? Same sample. Okay, so what happens? So we found that when the sample was heated in a hydrogen atmosphere, H minus is incorporated, substituting O double minus ion, okay, H minus. So because it's a hydrogen is stabilized, H minus is stabilized by a positive charge of the cage. Please remember that the electronic configuration of the H minus, two electrons are trapped in a 1s orbital. So the electron-electron repulsion is rather strong. So that when as UV photon is irradiated, so the 1s electron is easily photoionized from the H minus. So as a consequence, two electrons ionized from the H minus, and H minus converted to a H plus and combined with the remaining free oxygen ion to form a OH minus. OH minus is almost dead state. So the released electron move to the vacant cage and hop to the nearby vacant cages. As a consequence, we observe the electron conduction. Okay? So when such a conductive state is heated up to 300 degrees C, the reverse reaction occurs. So this reaction is totally reversible. Okay? So this result indicates that what is the role of H minus? H minus is just to provide an electron by stimulation of the UV photons. So this means that this crystal structure itself have an electron conductive pathway. Okay? The problem is how to dope an electron. So the H minus is just a photodonor, not essential, we thought. So we calculate the band structure of the C12F7. So the band structure is like this. So at first, please focus on these two, the valence band and conduction band. This is a very, very boring band structure. Framework oxygen contributes a lot. And vacant 5s orbital of calcium ion forming a cage wall is a dominant contributor. But please notice these two bands. So this band is a large, high distribution, dispersion. So we call this band come from as cage conduction band. That is to say, three-dimensionally connected cage form such a such a band. So this band is located below 2 eV from the bottom of the cage conduction band. This position is pretty important. If this position is high, almost impossible to generate an electron into the cage. Okay, so the cage structure has a positively charged. So by trapping an electron, so the cage structure becomes stable. Okay, then its level is come from oxygen 2p of the free oxygen ion. The oxygen ion is loosely bound. That's why this 2p level is a little bit high. So this means that when these free oxygen ion are removed and electron is injected into the cage conduction band, what happens? We may expect a lot of dispersion. So we may expect that almost metallic conduction occurs. So the problem is how to remove the free oxygen ion. Okay, so first I have to show the bond structure as measured by experiment. So this is bond structure determined by photo emission spectroscopy. And this is calculated band structures, valence band top and conduction band bottom. They're not so interesting, but please see that this band. This band is the cage conduction band. And this is reproduced by DFT calculations. But the problem is the calculation, not calculation by experiment. So that this is the data obtained by photo emission. So the photo emission is pretty sensitive to the surface. So that we adapted the hard X-ray UPS as excitation source. So that this is the bulk sensitive, not so surface sensitive. So that we can get the reliable data. This is the top of the valence band. This is the bottom of the conduction band. Please see that these small bump. So this data was obtained by Dr. Toda when he was the last year of the PhD course. He spent the whole day to get the one spectrum by using a synchrotron link. So the engineer of the researcher of the in charge of this link, please give up, almost impossible. But he insists this band should be here. And I accumulated 10 hours and at 10K and obtained this data. I love this data very much. Okay, this is a Fermi age. Okay, how to prepare the electron doped C12A7. So the result as the process, this is a typical sample we have adopted here. So the very simple idea. When the sample was heated, so the free oxygen ion moved along, and so that by using this behavior, we heated the sample with a titanium metal shot evacuated in SiO2 glass. When the temperature goes up and the free oxygen ion moved along and diffused away to the surface and combined with titanium ion. Titanium oxygen bond is pretty strong. So the titanium suboxide is formed on the surface. As a consequence, electron is injected. Okay, after that, surface titanium oxide layer is removed by mechanical polishing. So as a consequence, we can obtain C12A7 like this. If this reaction proceeds 100%, we may introduce an electron to the concentration of the 2.3 times the 10 to the 21st. Okay? So that this reaction proceeds 100%. I will show you. Okay, this is the data. And of course, before heat treatment, sample is well-known insulator. Temperature conductivity is below 10 to the minus 10. When as a part of the free oxygen is depressed by electrons, as the conductivity goes up, and when the electron concentration is 3 times 10 to the 19th, as semiconductors. And when this concentration reaches to 1 times 10 to the 21st, so the temperature independent. Okay, this means the Fermi level reaches to the mobility edge. After that, as metallic conduction occurs, please remember that the constitution of this material is CaO and aluminum. Both of them are typical insulator. But this is the metals. Okay? This is the same film of the sample. Little bit think brown, but the transparency is almost 80%. When this sample is cooled down, what happens? Okay? This is the data. So the metallic conductor, so when the temperature is cooled down, the resistivity is going down, and suddenly becomes 0. And this view graph of the light shows that the magnetic susceptibility against the temperature. When a whole sample of like this, 1 centimeter by 0.5 centimeter, as the whole volume become superconducting, as chi prime should be this line. So the experimental data is almost close to this line. This means that 100% of the bulk sample converted into superconductors. This is the evidence of the cement superconductors. Okay? I'll show the quite interesting story. Okay, so this is the heat capacity. Heat capacity is almost the same as expected by the BCS theory. Okay, this is also the good verification of the sample is the box superconductors. Okay, so when almost 206, as Bob Carver of the Princeton University described a brief note in Nature. He introduced the history of the superconductors. So many variety of sample, including silicon, have been converted into superconductor. So at low temperature, superconductor is not so rare material. Okay, but he closed this article by showing this sentence. Okay. Oh, this is a real story. Real. So please check the Nature this volume. Okay, so last year I sent an email. Last day of the 2008, last year, so many things happened. I wrote an email to Bob Carver, and we obtained the superconductors. So anyway, this is the news for you. So within 1 hour, I received the email from Bob. Absolutely, this is the correct superconductors. So I regret to describe such an article. Okay, but I have a family. I have to compensate the living expense, so it's impossible to retire. This is the real story. Okay, so the TC of this material is not so high, but please imagine this. Superconducting electron is a sphere, S electron. Okay, so please remember the S metals like sodium metal or the calcium metal. Neither of them exhibit a superconducting transition at ambient atom pressures. Only the S-band metal exhibits a superconducting transition at high pressure phase. So we check the correlation between our C12S7 and high pressure phase of the superconducting phase of the lithium. This is the case of the lithium. Okay, at ambient pressures, as BCC is the crystal structure of the metal lithium. When as pressure is applied, change to FCC, HR1, and eventually Cl16 phase. So this means that like a molecule. Okay, so the metallic structure is lithium-lithium distance is the same. But when the high pressure phase, lithium-lithium bonding is too close, like a lithium molecule. As a consequence, nanospace is created. Okay, so such a crystal structure is almost common for the superconducting phase of the S metal. This is the case of the lithium. Calcium is almost the same. Okay, so we may be surprised that the crystal structure of the metallic C12S7 and this superconducting phase have the same crystal structure. Okay, so the nanospace is a key to realize the superconductivity in S metals. Okay, and So people in Japan, the people say that the C12S7 metal is a good alternative for the ITO. I don't think so. And the conductivity of ITO is 1 order higher than that of the C12S7 metal. But the most unique feature of the C12S7 metal is a low work function. Work function means that the energy to extract the inside of the bulk to the vacuum level. Almost as ionization tendency you learn in high school. So the aluminum is 4.2, and the magnesium is 3.6 or maybe like this. So the C12S7 work function is almost close to the metal potassium. Low work function metal is chemically very active. Okay, if you touch the metal potassium by hand, what happens? Okay, chemically unstable, too reactive. But we can touch by hand to the C12S7 metal. Pretty chemically stable. And the melting temperature of this material is 1200 degrees C, very, very thermally stable. What happens such a thing? Okay, this is a band structure of the C12S7. So this is a cage structure of the C12S7 built from electron, and the electron is coordinated, an octahedral coordinated by 6 calcium ions. So this situation is almost the same as the electron traps at the oxygen vacancy in a CaO crystal. Built from the electron, this electron is coordinated by 6 calcium ions. And the band structure is the same. This is vacuum level is the same, and the conduction band bottom is here, and valence band maximum is here. So both materials are the same as band structures, except the cage conduction band. Okay, so the electron level in a CaO is here. Okay. On the other hand, electron level in a C12S7 cage conduction band is located here, 3.6 eV higher. It's a very, very simple reason. And the distance between electron to the nearby calcium is pretty close, this case. So compared to this case, the separation is extended by 50%. Okay? This is due to the strong tetrahedral aluminum bond is pretty strong. So aluminum 3 plus stretch as oxygen and calcium ion. So such a structure is pretty uncomfortable for electron. That's why this level is pretty high. But the beauty from as a whole, such a structure is rather stable because the tetrahedral aluminum form a rigid structure, like a cage. Okay, so the beauty from outside, this material looks like a refractory material. So when the water molecule want to come in, impossible. Such a cage structure invades the entrance of the outer molecule. So that's why this material is chemically stable and low work function. Electron in a space work as metals. Okay, but please imagine the conventional metals like potassium ions. Outermost electron of the sodium is stabilized the form of structure and as give electron conduction. Same electron and work as a structure builder and electron conductor. This case is different. Space in the electron in a space work as metals, and cage structure keeps such a rigid structure. It's a pretty interesting story, I think. Okay, we applied this material by using a low work function. This is example of, or What doesn't work? Okay, this is a demonstration of the electron emission from the sample. Okay, the sample is mechanically polished and apply a voltage and hits the phosphor pasted on the opposite side of the electrode. What happens? Okay, electron is coming in just by applying a DC voltage. So the sample is mechanically polished. Okay, very terrible thing. The professional very surprised to hear why such an electron easily come out. This is exceptionally low work function. Okay, so I'll show that another application. Okay, and have you heard the name of the resistive memory? Resistive memory is pretty simple. When applied voltage applied to the sample, when voltage exceeds the threshold voltage, sample change, resistivity drastically changed. So such a state can be applied to as a memory, so resistive memory. So the idea is pretty simple. Mobility of electron is much higher, several order higher than that of the O double minus. So that if we choose such a configuration, this is a sept21 metal, and the top surface is oxidized. So that this O double minus is in the cage and posted and deposited on the metals. Okay, so that when the DC voltage is applied to here, the free oxygen is moved to here, and the electron is come here. As a consequence, this state is electroconductive state, low resistive state. Okay, so that when the voltage is applied, switched from the high resistive state, low resistive state. So an opposite. This is like this. When the voltage is applied, so the suddenly change from the low resistive state, a high resistive state, to low resistive state. This is a memory, pretty good. Okay, the last application is the chemistry. Okay, so the formation of the carbon-carbon bond is pretty important, most important in organic chemistry. So the two forms of coupling reaction and reducing reagent is needed. So in organic chemistry, and so much amount of the solvent is used. But if we use the water as a solvent, and green process is possible. The problem is the activity of the reducing agent in a water solvent. So for example, the sodium, metal sodium, or the rare earth metal, when such a metal is dissolved in the water, what happens? Such a metal easily decomposes the water into hydrogen and oxygen. So that doesn't work as a chemically as a reducing reagent. So we apply the C12S7 in the chemical reaction, a CC bond formation, and like this, and aldehyde coupled, this is ketone, and coupled to each other to form a CC bond, and with two OH group. So that we introduce, we examined this reaction. So that to our surprise, that's a reaction occurred when the solvent containing water. Okay? If the solvent does not contain water, reaction doesn't proceed. So the most simple way is like this. When C12S7 metal is dissolved in the water, and the electron the cage is dissolved, and the electron is come out from cage to the water. As a consequence, this reaction occurs. But this looks reasonable, but no. Okay, we have calculated some dynamics. C12S7 is here, electron of the C12S7 is here, oxygen is here. The formation energy of the C12S7 is much stable than formation of the water molecule. So that if the thermodynamics is correct, C12S7 metal also decompose the water into hydrogen and oxygen. Nothing special, okay? But to check this thermodynamics, we did such a experiment, okay? This is a photograph. This is the experiment I did. So this is at first C12S7 metal, and when the water is added, so that in a few minutes, a lot of gas molecules come out. This is due to the hydrogen evolution. Okay, so the thermodynamics is correct. But so we did it a different way. So the first C12S7 metal is added, and the next aldehyde is dropped. And eventually water was added. Nothing happened. What happens? Nothing happens. Okay? This means that the aldehyde selectively adsorbs on the surface of the C12S7. Although after, or maybe after 1 week, such a black state still remains. So this means that this is a schematic view. So when the C12S7 and aldehyde are mixed in the presence of the water, the aldehyde molecule selectively adsorbs on the surface of the C12S7. And the direct coupling is possible. The electron is moved from here to here. And after that, OH minus 2OH is formed, so the reacted product is removed from here, water phase. So this is almost a unique feature of the C12S7. So the cement material is already like this. Cement material produce a gel layer. So the gel layer work a very, very important role in a chemical reaction. Okay, so the C12S7 is a metal, lower function metal, so that can be used as a electron emitter and how to say it's a memory and chemical reducing reagent. So a lot of applications are now possible. Okay, almost time. So the next subject is C12 amorphous oxide semiconductors. This is the history of the amorphous semiconductors. When I was high school, junior high school, photocopy appeared. So the photosensitive material used here was amorphous selenium. And 1953, oxide-based semiconductor appeared. This is Nature by Sheffield University. And chalcogenide, and now chalcogenide is used as active layer of DVD. But the most striking invention of the amorphous semiconductor is, of course, the invention of the hydrogenated amorphous silicon. 1975 by Spear and Lucomber in Dundee University in the UK. So the amorphous silicon is the first material which can control the polarity, N-type and P-type. And after that, as liquid crystal display appeared, so each pixel of the liquid crystal display is switched by thin film transistor or amorphous hydrogenated silicon. So the invention of the amorphous hydrogenated silicon created a huge market of the giant microelectronics. Giant means that large sized circuit fabricated on the glass substrate. Okay, huge market. So that now the people concentrating on new electronics called flexible electronics. Flexible electronics means that TFTs TFT fabricated on the plastics. So what's the difference? So temperature is different. This is a room temperature room temperature process. This is a high temperature process. Glass substrate and polymer substrate. So the many people think that the organic as a molecule semiconductor is much better. But I think that still inorganic is much better. This is my policy. Okay, so this is a material design concept I proposed in 1996. Okay, so this is a case of the silicon. So the mobility of the silicon for the n-type is 200. When the silicon becomes amorphous, what happens? So silicon is sp3, sp3 chemical bonding, so the bond is rather directional. So when silicon become amorphous, so the bond overlap between two sp3 orbital is not so good. So as a consequence, and mobility is dropped by 2 orders of magnitude. So this means that the amorphous semiconductor is pretty easy to have a large size thin film, but the electron transport is pretty bad. Okay, cheap but poor. This is almost a common sense of the semiconductor community. Is this always true? My answer is no. Covalent semiconductor is always like this. So the people believe that chalcogenide is almost the same. So the people working in electrical engineering and physics department is rather conservative. So in this world, so many variety of the materials there are like this university. Okay? So we focus on the oxide, ionic oxide. So the ionic oxide means that the nature of the band, nature of the conduction band is totally different from that of the top of the valence band. So the electron pathway and the hole pathway is a totally different nature. Okay? So we focus on the N-type material. So the bottom of the conduction band, which works as the electron pathway, is primarily composed of a metal component. So the oxygen is nothing to do. Okay? So if we choose it's a heavy metal with the electric configuration like this, so the spatial spreading of the metal s orbital is pretty huge. Contribution of p orbital is pretty small. So direct overlap between two metal orbitals is possible. Okay, so this is like a string composed of the metal ball. Okay, so the conductivity doesn't change in a stretched state and folded state. Okay, if we choose such a material, so almost the same electron mobility should be obtained. This is my idea. Okay, so the amorphous doesn't change. This is a stretch. Crystal is like a stretched state. This is a folded state. So the conductivity should be different so much. So this is a simple idea. According to this model, we examine the material. Okay, so this is the history of the amorphous oxide semiconductor we concentrated. So the 1995, I proposed a material design concept in the amorphous semiconductor conference, which was held at the Kobe. And this is no response until the 2003. Now, 2003, we fabricated the oxide TFT using a single crystal. But the single crystal is not so practical in meaning, so that we changed the single crystal to amorphous. And this paper appeared in 27th of the November of the 2004. So after that, the situation drastically changed. So so many papers appeared following our research. And the most the driving force of this area is the fabrication by a display company. So the leading companies such as, for example, the top bump printing, this is a professional of the e-paper, and as Canon, and the most striking contribution from Samsung, a giant of the display, and LG Electronics of the South Korea. So they fabricated a variety of the display. This is a typical example. So this is a photograph of the oxide TFT. We reported the 2004, and so in 2008, this is a photograph of the flexible OLED. Okay, I will show that how the electron transport differs from amorphous silicon. So that this is Hall mobility. Mobility is pretty low when concentration is low. So but when the carrier concentration goes up, suddenly changed. So that when the carrier concentration is high, mobility is high. So please remember the case of the crystalline silicon. Crystalline silicon is when the carrier concentration is high, low, the mobility is low. Now, with increasing impurities, the mobility is rapidly dropped due to the impurity scattering. This is totally wrong, totally different. Okay, and this is a Hall mobility as a function of the temperature. And when the carrier concentration is low, so the summary is activated type. When the carrier concentration exceeds 2 times 10 to the 18th, so they're almost constant. Okay, this is the first material which exhibits its metallic conduction. This means that the Fermi level exceeds the mobility gap. So such a situation was impossible in a conventional amorphous semiconductor. That's why so this material exhibits large mobilities. Okay, large mobility means that the band conduction occurs. In amorphous hydrogenated silicon, band conduction doesn't occur due to the tremendous amount of the defect state. Okay, so by using this feature, we fabricated the TFT like this. This is substrate is polyethylene, maybe. It's flexible, okay? And this is the TFT as performance, field very, very sharp. So the field effect mobility is 12. So the amorphous silicon case is 1. So the 1 order different. And this is the room temperature deposition just by sputtering, okay? By using such a very, very simple deposition process, we can get the 1 order higher as the mobility. And this is the data obtained by Canon. And the field of effect mobility is pretty large, and dispersion is pretty small. So each pixel works as almost homogeneous. Okay, so I will show that the defect state in amorphous and oxide semiconductor, and in comparison with amorphous hydrogenated silicon. So the defect state in amorphous oxide semiconductor is 10 to the 18th. Okay, please. This is the data of the amorphous hydrogenated silicon, 10 to the 21st, 3 order different. Okay, that's why when a carrier is doped, Fermi level can easily exceed such a defect level. This is totally different from the amorphous hydrogenated silicon. If we can invent a method to compensate such a defect state in amorphous silicon, we should have a large mobility even for amorphous hydrogenated silicon. But anyway, amorphous oxide semiconductor exhibits very, very wonderful properties. Okay, this is a view graph. So when the carrier concentration is low, it's impossible to overcome the potential well. But when the carrier concentration exceeds 3 times 10 to the 18th, carrier easily pass through, exceeding such barriers. Okay, and so this is a comparison with amorphous hydrogenated silicon. And this is the data of the amorphous hydrogenated silicon. So this is famous data by Spear-Lu combo in 1975. So when the electron is doped, the conductivity is increased, decreased, increased, but the Fermi level stop here, doesn't exceed this level. and whole doped is almost the same. So to explain this model, as Bob Street of the Xerox presented this model. That is to say, when a phosphorus is doped, phosphorus ion replaces the site of the silicon, and its electron is generated. But the generated electron is again trapped at the site of the silicon as a lone pair. Okay, so this means that cell compensation occurred. That's why Faraday level cannot exceed the mobility gap. Okay, so this is well considered model, but people believe that this model is always valid for any type of material. Okay, but the concept of the lone pair is limited to a covalent compound. This material, our material, is ionic material, nothing to do with the lone pair concept. That's why our material can exceed the mobility gap. Very, very simple idea. Okay, I'll show that as recent data. This is as OLED, which can be derived by our oxide semiconductors. Okay, this display was fabricated by LG Electronics, and the light one is public 12 inches of the OLED fabricated by Samsung Electronics. Very, very beautiful. I'm very surprised. Okay, so at first, our target was to apply our material as a backplane of the OLED. OLED is current-driven, not as voltage-driven. So the LCD has a large market, but the LCD doesn't need as high-performance TFT, I thought. But now the situation is totally different. So the demand for the LCD is totally changed because now the framework and frequency of the LCD is 60 Hertz. Now the next target is 120 Hertz. Now the most advanced LCD is four times faster, 240. Okay, 240 means that the frame frequency is so high, so it looks smooth. Okay, and also size is much increased. Okay, so the next feature, next generation, the 3D LCD is now as booming. So the to drive such a new type of LCD, high performance LCD is absolutely needed. This is data by Samsung, maybe Samsung Electronics, and now the current LCD is right here, the 60 Hertz, and the size is 70. So the 0.5 mobility of the 0.5 is enough, but as performance is moved from here, so the mobility of the 1 or 2 is needed. Okay, amorphous silicon's case, and the commercially available, and the mobility of the is 0.5. 0.1 is impossible practically. Okay, so the new type of the TFT is absolutely needed to meet the new trend of the LCD. That's why oxide, amorphous oxide TFT is now booming. We're very surprised. This is not our planned. This is totally beyond our imagination. Okay? Okay, this is a device as reported so far by using our oxide TFT. So this is our data, 204, and this is e-paper and flexible e-paper and flexible OLED, OMOLED, LED, and I love cat very much. Anyway, so this is the active matrix LCD. Okay, so the active matrix LCD is now age of the new as semiconductor, new as TFT. I don't know. That's as the next 5 years is pretty important. I don't know. But anyway, the last subject is iron-based superconductors. Okay, so almost 1 hour passed. Can you give me the more? 15 minutes. 15 minutes is enough. Okay.
Nobody's leaving.
Okay. 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 This is the history of the superconductors. Okay. So do you know who discovered superconductivity? Cameron Olness of the Leiden University, Dutch, discovered the superconductivity. So when he measured the electrical resistivity on mercury, 1911s. Okay, 1911s. After that, Tc is gradually increased. Okay, and until 1986. 27 is the maximum. Okay, so the people call the sealing of the BCS. Okay, so the many theoretical people propose a model why is 228 is the limit of the superconductivities. Okay, but after that, suddenly 1986, and Bedros and Muller of the IBM Zurich discovered cuprate copper oxide based superconductors. Okay, after that.
Sounds like it goes off after an hour.
Okay. Okay. So, but okay. So that's the Tc is dramatically increased. Okay. After 1993, almost saturated. So the people believe that this is almost the end of the superconductivities. Okay, no, so many report predict if this trend continued, the research of the superconductivity died until the 2015. Okay, so to our truth, almost by chance, we discovered iron-based superconductors, 2006. After that, as the Tc is dramatically increased, now the maximum Tc is 57s. Okay, and as introduced in his talk, and more than 1,000 of paper, printed paper, have been published to date. So what is the proposal of the limit of the BCS theory by theorists? Okay, so the first principle of the superconductive research is don't believe the theoretical people. This is the first principle proposed by Dr. Matthias, very famous rule. Don't believe the theoretical people. But someone said, please pretend to hear the theoretical people. Maybe this is correct. Theoretical people is rather clever, but don't believe the truly. Okay, this is a property as a comparison among the three typical superconductors: iron-based superconductors, and metallic superconductors, and cuprate. So the highest is highest Tc is like this. The cuprate is the best, but the maximum Tc is like this. But the iron-based superconductor is quite interesting. Is pretty strong to the high magnetic field. So superconductivity disappeared when high applied field is applied. High field, magnetic field applied. Also, the critical magnetic field is called Hc2. So this is pretty high. So this material have a potential for application of superconducting wire for NMR, nuclear magnetic resonance. But still, the research is just started, 1 hour, 1.5, so that nobody expects the future. Okay, so I'll show that the why we discovered this material. It's a very, very simple material, simple story. Our target is P-type transparent oxide semiconductor, as reported in 1997. Okay, but that copper aluminum oxide is the first material we reported as a P-type oxide semiconductor, but the performance is not so good. We feel to improve the property. So the top of the valence band is oxygen. So the oxygen and to make a covalent band, oxygen 2p and copper 1 plus. This is good, we thought in 1997. But now the overlap is not so good. To have a large overlap, we introduce chalcogenide in place of the oxygen. But 3EB is absolutely needed to keep transparency. So we selected the two-dimensional material like this. This is a layer of the copper sulfide, and the copper is 1 plus ion. Okay, so the net charge is double minus. To compensate the discharge, we adopted the lanthanum oxygen layers with +2 plus charge. So the minus charge and the plus charge layer are alternatively stacked along this direction. Okay, when lanthanum is replaced by 2 divalent cation, the hole is injected. But due to the band offset, the hole is moved from here to here. Impurity is here, the hole is located here. So that we can avoid the hole impurity scattering. So that we may expect a large mobility. Okay, as a consequence, first we fabricated a good quality thin film, and we obtained the room temperature stable exciton and P-type conduction, and eventually we fabricated the blue LED. Well, this research is successful. Our next target is to realize magnetic semiconductors. So the copper 1 plus is a non-magnetic ion, 3 closed structures. We need the open shell structures. So that we need a divalent cation, such as Fe2 plus or manganese 2 plus. So that we replace copper 1 plus ion with divalent transition metal cation, so that we have to change the chalcogenide ion with 2 minus with nictide ion with -3 ion. So that we check the crystal structure, material, by within the framework of this crystal structure. We found that so many material already reported. So we synthesized these material. Okay, so from manganese to zinc, we synthesize lanthanum as transition metal chalcogenide, nictide. So this is the result. Manganese is a semiconductor, and the antiferromagnetic semiconductor. Iron is a superconductor. As cobalt is a metal, ferromagnetic metal, and nickel is a superconductor, and zinc is of course a semiconductor. So please see that when number of the 3D electron of the transition metal cation are even, superconductor transition is observed. Okay, so the copper, iron, cobalt, and nickel is well known as ferromagnetic metals. Okay, but 2 of 3 are superconductors. Okay, so in a chemist, as the property of the element is totally different from the compound. This is a kind of the common sense for the chemist, but physicists is not so common. That's why physicists are excited to this material. So for me, the superconducting cement is much exciting. Okay, anyway, but very simple reason. Okay, so this is also quite interesting. Okay, this is a comparison between phosphorus state and arsenic state. The phosphorus state is without doping. When the samples cool down, superconductivity observed. So that we replace the phosphorus ion by arsenic. So the arsenic case when the temperature go down and like this. At first, we as a student in charge of this material thought this is due to the superconductive transition. Okay, pretty high. If this is true, this is the highest TC. Okay, so but eventually this is not a TC. This is a magnetic transition. And so we doped the electron carrier by replacing oxygen with fluorine. So when the fluorine is doped, this transition disappears and superconductivity come out. Okay, so the electron doping is very essential. Okay, as non-doped state we call the parent material. Parent material is not a superconductor. Okay, this is a parent material superconductor, but TC is low. This is as parent material is not superconductor, but when the carrier is doped, that's a high TC. Okay, this is almost pretty much the case of the cuprate. The parent material of the cuprate is insulator, not insulator. When the hole is doped, superconductivity come out pretty close. This is almost the same. Okay. I'll skip. Okay, like this. Phase diagram is like this. So when electron, the parent material is antiferromagnetic metals. Cuprate is an antiferromagnetic insulator. This is metal. This is totally different. But the antiferromagnetic state is the same. But when carrier, this is a case of the electron. Electron is doped. And so antiferromagnetic phase disappear, and at this boundary, superconductivity goes up. Sometimes, like this. So the superconducting state and antiferromagnetic state looks coexistent. So this is not a true coexistence. I'll show the data. This is almost the same. That's no oxygen, this layer. And 111 is almost the same. 111 is cation layer is almost no. So almost no. And this is the electronic structure of the this material. So the Fermi level is here. The Fermi level is dominated by 3D ion electron. So this is a superconductor of the ion, absolutely. Okay, so each of the 5 structures containing a common structure, like this one. Fe is 2 plus square lattice. This layer is commonly contained in the superconductors. Okay, so very, very simple structure. So when I saw this, the history, so various events I remember. So it's not so good. So anyway, so this is the progress of the ion-based superconductor. The date of abscissa is the paper is submitted, or the paper is posted on the website. The superconductive research publication in a printed journal is not so important. Okay, so I didn't know such a custom in the superconductivity community. When someone found a quite interesting result and wrote a paper and posted on the Condumat. Okay, so I asked some guy, my friend, what is Condumat? He said he's a pretty good scientist. Condumat is a rumor channel on a superconductivity society. I don't like a rumor. So I ignore it. This is totally wrong. So day by day, so people posted on the new result around here. So June 13 of the June, one day, 16 papers were posted. This is the maximum record in the history of the Condumat. So almost incredible. Okay, so this is the history. Okay, okay, no. Okay, I'll skip the anyway. Okay. I still believe iron is hot. So there's so many chances in front of us. So okay, please remember that 2 years ago, nobody believed that the iron-based superconductor become a good candidate of the high temperature superconductors, including us. Okay, materials research is much exciting than we expect always. Okay, so this is a summary of my talk. So this modern building is composed of the 3 materials: iron, glass, and cement. So each of them is believed to be a building structure material. Nobody believes that such a material can be a good electroactive material. Okay, if such a abundant material can be converted into a high performance material, so that our future is bright. Okay, we using an abundant element so if we can obtain a new functional material by using an abundant element, our future is very, very good. So the key is how to design the nanostructure. Okay, this is a typical example. Okay, this is the last view graph. So this is a world map. This is very, very familiar for Japanese because Japan is located here. This is a world map. This is Eurasia continent, and Europe is here. Europe is here, and the United States is here. Okay, so this is like a Mongol. So we are Genghis Khan. We started from Mongol and cultivated the frontier, and Japan, Korea is a small country, we ignore us, and proceeded to here, and we arrived at Vietnam, so we found a good application of as a flexible display, and after when we arrived here, we found a totally new phenomenon, that is the calcium and aluminate can be converted into metals. So the C12S7 metal, discovery of the C12S7 metal is like a discovery of Australia. Okay, and after that, so we continued the research, and we found a new superconductor at first. And the discovery of the iron-based superconductor is like a discovery of Hawaii, but totally wrong. Now the people call it, this is almost a discovery of North American continent. So we are now landed in United States. So next is Canada. Okay, that's why I'm coming here. But anyway, material research is always exciting than we expected. Thank you very much.